Okay, the next part of this class, I will be starting. So I will recall for theta equal 0. Okay, when theta is equal to 0, when this theta is equal to 0, when we assume that this theta is 0, then at that time, this n will be in the same direction as the direction of the force. Okay, okay, so that is the only case when our area will be in this direction. Okay, when our area vector will be in this direction and this force vector will also be in the same direction. Okay, so at that time, as far as the value of sigma is concerned, the value of sigma will be for theta equal to 0. So this cos 0 is 1, 1 plus 1 is 2. That will be equal, normal stress will be F by A. Fine. And when we talk about the shear stress, sine 2 theta is 0, sine 0 is 0. The value of tau will be equal 0. Okay, so whenever you have a case like this, whenever a machine element is like this, whenever you have a machine element like this, okay, and say for example force F is acting on this machine element and its area is, say for example, A. Okay, the area vector is also in the same direction as the direction of this force, then you should directly say that on this face there will only be normal stress given by F by A. There will be no shear stress, because it's quite easy to say, because the force vector and the area vector are parallel to each other. There will be only the normal stress, no shear stress on this face. Fine. The case 2 is when theta is equal, when we have theta equal 90 degree. Okay, this is a very important case for us. When you talk about theta equal 90 degree, so you have, as far as the area is concerned, your force, you say that your force, your theta is 90 degree. At that time, it means the force vector and area vector are perpendicular to each other. Fine. How that happens? What you have to do, you have to move this area. This area is to be moved in such a way, you have to rotate this area in such a way, such that the angle that it subtends with the force F is equal to 90 degree. Fine. That's only the case. That will be the case like this. You have for theta equal to 90 degree, the case will be like this. Fine. The case will be like this. So the area vector is in this direction. Fine. Or let me rotate this force only. Let's rotate this force. Sorry, keep the force in the same direction. F direction is the direction of the force. Okay. And the area vector is at 90 degree. The area vector is in this direction. So you are talking about this area. This is the area vector. Fine. That is, you try to recall what's happening. So as we are rotating this, as we are rotating this, we are keep giving it now, instead of theta equal to 0, we are giving theta equal to 90. We are giving theta is equal to 90. Fine. Theta is equal to 90 means when this area vector will be rotated like this, when it will rotate like this, area vector. So it means your area is like this. Your area has to be like this. Area has to be like this. Only then it can have a vector, area vector will be in this direction, such that between area and force, the angle will be 90 degree. Fine. That is the case like this. So area is here, our area is here, and our force is acting on this area. Our force is acting on this area. Okay. And our area vector is somewhere else. Fine. The effect is, what will be the effect of this force on this area? Okay. Will it create a shear stress or normal stress? Fine. We say we apply this formula. So theta is 90, cos 180 is minus 1. So it's 1 minus 1, which is 0. Therefore, on this area, there will be no normal stress. Sigma is equal to 0. Fine. Your theta is equal to 90, sine 180 is 0. Therefore, tau is also equal to 0. Tau is also equal to 0. Fine. What is happening? We are applying force on one area and we are taking another area into consideration. Fine. Therefore, there will be no normal stress on this area, because on this area there is no force acting. F is equal to 0. Therefore, there will be neither normal stress nor there will be shear stress. Fine. So this is very important conclusion here. So when you take theta equal to 90 degree, at theta equal to 90 degree, your area vector is in one direction and your force vector is in another direction. Fine. Uh, the area which we are considering here is not an area over which some force is acting. Therefore, there will be neither normal stress nor shear stress. This is for theta equal to 90 degree. Now, similarly, we can talk about theta equal, say, for example, 180 degree. Fine. When you have theta equal to 180 degree, when this n becomes 180 degree, so it means this area vector is in this direction and force vector is in this direction. At that time, the angle between n and f is equal to 180 degree. Fine. So the case will be theta equal 90 degree will be like, similarly, you can talk about theta equal 180. The case will be like this. So we have an area, we have area like this. Force is acting in this direction and area vector is in this direction. Area is in this direction. Fine. The angle between them is 180 degree or pi radians. Fine. So we can simply use this formula. Okay. On this area, now, okay, I will, on this area now, on this area, force F is acting in this direction. Okay. While as the area vector is in the opposite direction. Fine. So what will be the normal stress? Sigma is equal. So this is cos 180, that is cos 360. Cos 360 is 1. You have 1 plus 1, which is 2. 2 and 2 will cancel. The normal stress will be F by A. How much will be shear stress? Tau is equal. You have theta equal to 180. Sine 360 is 0. Shear stress will be 0 on this area. Fine. Similarly, you can take different areas. Fine. When you take an area, like this case is peculiar case. You have area in this direction. Okay, you have area in this direction, while as the force is being applied in this direction. On this, we are applying force on this area in this direction, right? What is the effect of this force on this area? It does not have an effect at all. Normal stress and shear stress is equal to 0. Similarly, we can go ahead and talk about when theta is, say, for example, 45. We can say when theta is 45, when theta is equal 45 degree, at that time normal stress is equal, this is cos 245, this is cos 90, cos 90 is 0, it becomes F by 2a. And how much is shear stress tau? Shear stress tau for theta equal 45, this is 45 into 2 is 90, sine 90 is 1, it is F by 2a. It means sigma is equal to tau is equal to F by 2a when theta is equal to 45 degree. Okay, what does that mean? When the value of this theta is 45 degree, when the value of this theta is 45 degree, at that time the normal and shear stresses are equal. The normal and shear stresses are equal whenever theta is how much? Whenever theta is 45 degree. Fine. So this is what we can talk about the stresses on the inclined plane. Let me take an example from your book. Let me share their book with you. Uh, look at this question of a book. This question says, talks about the, uh, we have a member AB, okay, and this member is attached with another member AC. The total span is 200 mm. Fine. We're applying a load of 3 kilonewton at a distance x from the member AB. The cross-sectional area, the rod has a cross-sectional area of 400 mm square, and contact area at C is 600 mm square. That is, the area of cross section here is 600 mm square, 600 mm square, and the area of this rod is given as 400 mm square. Fine. Now we're applying a 3 kilonewton load here. The question says, how much is average stress developed in the rod AB? How much is the stress developed in the rod AB? First of all, before we do these types of questions, what's very important is to draw the free body diagrams. Okay. Free body diagram means, first of all, if we are asked to calculate how much is the stress in rod AB, how much is stress in rod AB, we should be knowing how much is the force in rod AB and in which direction, divided by area of rod AB. Area of rod AB is given to us, but we are quite unfamiliar with the force. We don't know how much force is acting in the rod AB. We don't know how much force is being produced in the rod AB. So first of all, if we calculate the value of this force in the rod AB and we divide it by the area of the rod AB, we'll be able to calculate the stress in the rod AB. Now, how to do these types of problems? I think since the time of this meeting is over, that we'll be doing hopefully in the next class.